Big test coming up tomorrow, the second to last test of the year for us. This one's on circular motion and gravitation. We had a practice test that we gave you yesterday in the hopes that you would have a chance to do it last night so that we can go over it today. We're going to spend some time going over that test today, see where you need a little bit of help, okay, see where your strengths are. And you're going to use that to focus tonight on what you really need help studying on tonight, okay, what you really need to focus on studying on tonight. All right, let's go right out of here, guys. Question number 1. It says a 1,200 kilogram race car makes 3 revolutions around a circular racetrack of 300 meters in a time of 2.50 minutes. Determine the centripetal acceleration, the force, and the coefficient of friction between the car tires and the pavement. I think clearly if we want to find centripetal acceleration, we're going to use A is equal to V squared over R. I don't think that that's rocket science here, okay? I think that everybody's going to get that. The issue here is that we don't have speed, so we've got to find speed. If we write down the equation, A is equal to V squared over R, and then we say, look, we got to find speed. Suggestions as to how we might find that? Suggestion, because there's only one way we can do it. Yeah, okay. Yeah, we're going to say V is equal to 2 pi R over T. Now, here's what I saw some people do yesterday. A couple people actually do this yesterday. They're saying, look, we got the number of evolutions. We have the time. Let's find the frequency. The frequency is the number of evolutions, 3.00 revolutions, divided by the time of, it would be 150 seconds. We get the frequency from there in hertz, and then we're going to say T is equal to 1 over F to get the period, and then plug it back into that equation. Does that work? Sure it does. Is it the quickest, most efficient way to do it? Not at all. Because if you're able to find frequency by saying 3 over 15, and then find period by taking the inverse of that, why wouldn't we just say period is equal to 150 seconds over 3.00 revolutions? Gives me 50. Does that make sense? The period is the time per revolution. Frequency is revolutions per time. And sometimes it's important to get frequency, but not here. We don't need the frequency here. We need the period. So if you can get it directly, why not do that? Now, having said that, if you calculated it the other way, that I just had written down and erased, would you get full marks for that? Of course you would. It's right. It's an extra step. It's work that you didn't have to do, but it's right. Okay, you'll always get marks for correct work. So my period is 50 seconds here. 2 times pi times the radius of 300 meters divided by the period of 50 seconds gives me 37.6991. 37.6991 meters per second, which we're going to turn around and plug into here. 36 squared, don't forget to square it, divided by R is, we do the math there, we get 4.74 meters per second squared. How many people got that? Hey, listen, you got to figure, guys, this is way back to the beginning of the unit where we did a few problems like this, right, where we're combining the period with the speed, with the centripetal acceleration or force. You got to figure there's a real good chance of seeing something that's like this on your test tomorrow. Okay, a very good chance of seeing something that's like this on your test tomorrow.
How good?
A very good chance. Yes. Yes. Thank you for that question, Nathan. It's a very good chance that you'd see something like this. Now, how would we find the centripetal force experienced by the car? We could do this almost from scratch. We could say F is equal to mv squared over R. M times, well, we could find V again, but we already found it. M times V squared divided by R, solve for it, do your thing. Hey, but you know what? F is also equal to M times A. So you don't have to go back to scratch and do it from scratch. You can say, we know what A is. We know this acceleration is 4.74. So if we want, all we have to do is say 1,200 times 4.74 meters per second squared gives us a number of 5.68 times 10 to the 3 newtons. Okay, how many people that did this question went back and said F is equal to mv squared over R? Okay, how many people did what I did there? Okay, what you did, what a lot of you did there, I would say is a little bit more work, but not much, right? Unless you recalculated speed and recalculated period, then it's quite a bit more work, right? But if you just said F is equal to mv squared over r, it's a tiny bit more, but not much. I wouldn't lose any sleep over that. Either method, I think, is good there. You get the same answer in both cases, right? Doesn't matter which way you do it. Okay, finally, C, this is a good question. The coefficient of friction between the car tires and the pavement. There is only one force that's causing this car to go in a circle, and that force is friction. If there was more than one force, we'd need to say F net is equal to the sum of the forces. If there's only one force, then we're going to say F net, or the centripetal force, is equal to that one force. Okay, we've done problems like this before. In fact, we've done problems at literally yesterday when we were dealing with satellites, and we'll talk more about satellites, review that a little bit more later on. But when we were dealing with satellites yesterday, we were dealing with problems where the centripetal force was caused by one force. Yesterday it was gravity, today it's friction. We're going to set frictional force equal to the centripetal force, just like yesterday we set the force of gravity equal to the centripetal force. If there were two forces, then it would be Fc is equal to F1 plus F2. But there's not two, just one, friction. So we're going to say mv squared over r is equal to mu times the normal force. And of course, the normal force normally, usually, is equal to m times g on a flat horizontal surface. Masses cancel because it appears in both terms on both sides. Solving for coefficient here, we know the speed, 37 point, you can rearrange this, I guess. We're going to say mu is equal to v squared over g times r. 37.6991 divided by 9.81 times, what was r? 300? Okay, we do our math here and it works out to be 0.483. Does that seem like a reasonable number for the coefficient of friction? Sure. What do we usually see? Somewhere in the range of 0 to 1. 0.483 falls right in the middle there. I would say, honestly, that's actually probably a little bit low for a real coefficient of friction. Usually it would be somewhere in the range of 0.6, 0.7, but still reasonable. How many people got that? How many people got 100 so far on the test, on the practice test? Okay. Nathan, you didn't? So you didn't, did you say? Oh, you did. 2. A 1,200 kilogram roller coaster is moving around a vertical loop of radius 12.0 meters. Determine the minimum speed that it needs to move so that it does not fall out of the loop. So here's the vertical loop. Here's the roller coaster at the top of the loop. Although, you know what? Really, we don't even need to draw in the roller coaster, right? It's a guy standing upside down. It's a roller coaster. It's a set of keys on a string going upside down. It doesn't matter what it is. In the end, there's two forces acting on that roller coaster car or those keys or whatever it is. Fn and Fg. Some of you might say, well, wait, isn't there a third force? Isn't there centripetal force? Yes, there is centripetal force. Why am I not calling that a third force? Why is the centripetal force not a third force? Yep. Yeah, it is an actual force, but it's not a force on its own. The centripetal force is these two forces. So it's kind of like saying, remember when we did those inclined planes and we had the normal force and force of gravity and then F parallel? And we said F parallel really is just the normal force and gravity combined? Well, here the centripetal force is really just normal force and gravity combined. Okay, so we're not gonna say Fn, Fg, and Fc. We've already got Fc here. It's Fn and Fg combined. All right, so let's say F net is equal to the sum of those forces, Fn plus Fg. mv squared over r is equal to Fn plus Fg. But, hey, wait, missed something here. If we're traveling at minimum speed, something disappears. Fn disappears. Okay, not because it cancels, but because its value is 0. So we're going to say mv squared over r is equal to fg, or mv squared over r is equal to m times g. M's cancel. Plug in your values. Looking for v. R is 12 meters. Let's put a negative out front because centripetal force is downward toward the center. Equals negative 9.81. Solve for v there. Take the 12 up by multiplying, square root. And when you do that, you get 10.8 meters per second. Two, determine the force on the track, acting on the roller coaster car if the car is moving at twice the speed when it's at the top and when it's at the bottom. So here it is at the top, Fn and Fg. This time Fn is not 0 because you're not going the minimum speed. Hey, listen, when you're at the top of the circle, Fn and Fg are always what we draw there. When it's in the very specific case of it being at the minimum speed, then Fn is equal to 0. But all other times, Fn is something. Something here. Let's plug in some numbers here, guys. M was 1200. V was V was actually not 10.8. V was 21.6. I've actually got 21.6998. If we took the unrounded version of this and doubled it, it's 21.6998. Divided by R, 12 meters. Now we got to worry about some signs here, negatives here. This is negative because its centripetal force is down. So is this. Gravity is always down. So what I want you to do here is get a number for this. Get a number for this. Take this over to the other side by... It was you that I was talking about this with, right? Take it over to the other side by... Keep going, dividing, subtracting, adding. Yeah, there you go. There you go. It's a negative value on the right side, so it's like subtracting. So let's take it over to the left side by adding. Okay. When would you divide it by the other side? If it was multiplied by Fn, right? Not if it's subtracted from it. Okay, solve for Fn there. And it works out to be, make sure you can get this, works out to be negative 3.53 times 10 to the 4 newtons. Hey, if you don't get a negative value there for Fn, did you make a mistake? 100% absolutely yes. How do you know it's got to be a negative value for Fn there? Yep. Because it's acting down, right? The picture that I do at the beginning shows me that it's acting down. We know that we've got to get a negative value right from the start. If we don't, we made a mistake somewhere. What about when the car's at the bottom? The bottom of the loop here. What would you expect to get here for Fn? Negative or positive? Positive. Right? We draw it, it's acting up. We're going to start off the same way other than the diagram. Fn plus Fg. And then we're going to say mv squared over r is equal to Fn plus Fg. Let's see here. Once again, we got 1200 times 21.6998 squared over 12. Plus the force of gravity. Let's worry about negatives this time. Gravity is negative because it always is, but the centripetal force acts toward the center, which if you're at the bottom, is up from you. So it's going to be a positive value. It means we're going to get a different number here. Fn works out to be this time 5.89 times 10 to the 4. Bigger. Do you expect that? Yeah, of course you would expect that. Okay, let's think about an analogy for a second here. Okay, you're in a tug of war. you're in a tug of war, and you are the normal force. The person against you is the force of gravity. So we're in a tug of war. Okay, you're FG, your name is FG, my name is FN. Okay, let's say that we're in a normal tug of war and we're pulling against each other here, right? Okay, so you're pulling that way, I'm pulling this way. Okay, I have to pull pretty hard to beat FG, right? Because FG is pretty strong, right? So I have to pull pretty hard to beat him. But let's say it's it's the new age tug of war where nobody's a loser, everybody's a winner, everybody gets the participation ribbons. So now we're gonna just bow the rope around. You're going to be at one end, I'm going to be at the other end, but we're going to both pull in the same direction. Do I have to pull as hard now? Okay, when I'm pulling in the same direction as FG, then I don't have to pull as hard as when I'm pulling in a different direction. Okay, look at this. I'm pulling in the same direction as FG. I got to pull 3.53 times 10 to the 4. But here I'm pulling against FG. When do I have to pull harder? When I'm pulling against FG, right? Okay, so of course we expect a bigger force at the bottom than we get at the top. Always. Normal force will always be bigger at the bottom than at the top, and it's always going to be positive. So if you don't get a positive number, and if you don't get a number that's bigger, you made a mistake. Check it. And finally, C. C was a little unclear, actually. Somebody was asking me about this earlier. It might have been Bree. Says, determine the apparent weight when the car is at the bottom of the loop. And I said, even though I made this practice test up last semester, I couldn't remember what I had meant, and it wasn't real clear in the way that I had worded it. Determine the apparent weight of the car when it's at the bottom of the loop. When? Like when it's at the bottom of the loop moving the minimum speed or double the minimum speed? What did I mean? Okay. Well, as it turns out, when I look at my answer key here, Bree, I meant for it to be when it's traveling at double the minimum speed. So we're continuing on from question B, where you're traveling double the minimum speed. Does anybody know what the answer would be? Real quick, without doing a calculation. What's the apparent weight, Nathan, number 2, if we're at the bottom of the loop, okay, traveling at double the minimum speed? 5.89 times 10 to the 4. Why do you say that? Same as the normal force, yeah. The apparent weight is the same as the normal force. If I've already found the normal force, then we're done. Now, if the question said, what's the apparent weight when the car is moving at 36 meters per second, then I'd have to go through that procedure in this one again with a different speed, right? Okay, but same thing as normal force. If you've already found it, you're done. But I think I told you that when we were looking at it that I thought that I had meant at the minimum speed. Okay, so if you did it that way, you're going to get a different number than that. That's fine. Okay, you should expect to get a number that's smaller than that, right? Because you're traveling at half the speed. Not a force that's half the force, but a force that's smaller, definitely. Okay, did you do it that way?
Yeah.
What'd you end up getting? Did anybody do it that way, assuming the minimum speed? That seems like a reasonable number to me, so I think you probably did it right. Yeah. Determine the gravitational field strength produced by Jupiter at a point on the surface of Jupiter, 800 kilometers above the surface of Jupiter. Is Jupiter a producer or experiencer? Is it causing the field or is it experiencing a field? Yeah. I mean, really and truly, it's both, right? It produces a field of its own and it experiences a field caused by other planets and by the sun. But in this context, it's definitely a producer. We know something about Jupiter. It's the producer. Let's use the producer equation. The mass of Jupiter is 1.90 times 10 to the 27 kilograms, almost 1,000 times bigger than the mass of the Earth. The radius of Jupiter is also bigger, however, 7.15 times 10 to the 7 meters. And that's on your data sheet as well. Or it's on a table that you'll be given on the test, whichever. So we got a bigger mass and we got a bigger radius. What do you expect to get for gravitational field? The mass causes it to be bigger, but the radius causes it to be smaller. It's a balance, right? Do the math there, 24.8. It's bigger. So the field strength is bigger than that on the Earth. Why? Well, the radius is bigger, but the mass is way bigger. So the mass ends up having more of an effect than the radius is. "800 kilometers above the surface." Okay. I'm going to do something here. I want you to yell stop when I've done something wrong. What? Stop. I didn't do anything. Sorry? That's what I'm doing.
You should probably convert it, right?
Convert it to meters? Okay, good. Bree's right. I should convert that to meters, right? Okay, 800,000 meters, right? All right. You caught me, Bree. What? I'm also supposed to add the radius of the Earth. Good. So it's 7.15 times 10 to the 7 plus 800,000 meters. Joseph, why did I have to add the radius? Bree, you're absolutely right. Got to convert that to meters, right? 100%. Why do I have to add the radius of Jupiter to it, though? Yeah. The field strength at a certain point above the surface is the distance from the center of the planet to this place. Okay, and that's going to be the distance above the surface plus the radius of the planet. Here's what you should do. Calculate that number, press equals, square it, press equals, and then do the rest of the math there. It works out to be 24.2. So not that much less, right? Remember we've said before, gravity on the International Space Station is about 9 or 9.1 newtons per kilogram. Almost as much as it is on Earth. It's because there's a few hundred kilometers. It makes a difference in gravity, but it doesn't make that much of a difference. Okay, you got to be a long way away from a planet to really decrease gravity to a negligible amount. We were solving satellite problems yesterday, looking for the speed of a satellite, height of a satellite, whatever. Why did we not set this equal to something? Like, what's the difference between what we did yesterday with the satellites, where we set FC equal to FG, and these problems, where we're just saying G is equal to GM over R squared? Why would we not set FC equal to FG here? Yeah. We don't even know if there's an object experiencing the field, let alone if that object is moving in a circular path, right? So we can't set that equal to each other. We can't do that. Again, this is what it is because we've got a point in space where we're trying to find the field strength. It has nothing to do with an orbiting satellite. Nothing at all. 4. Determine the gravitational force experienced by a 300 kilogram UFO 800 kilometers above the surface of Jupiter. Well, trying to find force, remember, we're not going to use a field equation. We could say this. Is that okay? M1, 300 kilograms. M2, the mass of Jupiter. R being this distance here, 7.15 plus 800,000. Can I do this? F is equal to mg. If I'm allowed to use this equation here, above the surface of Jupiter, what was the point of ever learning this equation? If I can say F is equal to mg, why do I need a more complicated equation that gets me the same force? Good. The gravitational field on Earth is about 9.81, although we've seen that the number we usually get when we deal with the average radius of the Earth is about 9.78, right? The value we usually use is 9.81. Normally, we wouldn't know 800 kilometers above the surface of Jupiter what the field strength is, but we do this time because we just found it. We do that math, it works out to be 7.27 times 10 to the 3. If you didn't spot that, that's okay. If you didn't spot that, then calculate the force this way. Use the mass of Jupiter, use the mass of the UFO, use 7.15 plus 800,000 for the radius, and guess what you're going to get? $7.27 times 10 to the 3. Five, the International Space Station orbits around the Earth at an altitude of 360 kilometers. What's the orbital speed and the time that it takes to make one revolution around the Earth? Well, this is what we did yesterday, right? This is the satellite problem. This is where FC equals FG. This is not just the space station sitting there finding the field strength. This is how fast is it moving as it orbits around the Earth. You guys remember this? Who wasn't here yesterday? Okay, who wasn't here yesterday? Jared, are you here? If you weren't here yesterday, it's especially important to pay attention to this right now. This is one question, but it's pretty representative of what we did yesterday. So we got a satellite with an object orbiting around the Earth. FC equals FG. Cancel out one of the masses. Cancel out one of the R's. Hey, what mass did I cancel out there? What mass remains over here? Yep, the producer. So it's going to be V squared is equal to G times the mass of the producer over R. We're looking for V, so it's going to be the square root of GM over R. Now you got to be careful with R here. It's the 360,000. Not going to make that mistake of not converting again. Plus the radius of the Earth. Do the math there, works out to be 7.69 times 10 to the 3 meters per second. 7,700 meters per second. Man, think about that. How fast is it going? I don't know, about 75 football fields in 1 second. 75 football fields in 1 second. Why do the people on board not feel it? Yeah, it's not changing speed, right? It's staying at 7,600 meters per second. If it all of a sudden stopped or slowed down dramatically, then they'd fly against the wall, right? They'd get pinned against the wall. The time that it takes to make one revolution around the Earth. How about this? Isn't T what we're looking for here? The radius we ended up having was 6.74 times 10 to the 6. These two numbers combined. Divided by the speed, we just got 7.69 times 10 to the 3. .51 times 10 to the 3 seconds. Hey, look at that number. About an hour and a half. It takes an hour and a half for the space station to go around the Earth. Remember yesterday when I showed you that website with the space station sightings? There might have been a sighting at 3 in the morning. When was the next sighting? Yeah, about 4:35, something like that in the morning. An hour and a half-ish later on. And then there wasn't another one. Then they didn't have another one at 7 or 8:30 or 10 or noon time, right? Why didn't they have another sighting at noontime? Doesn't mean the space station's not there. We just can't see it. because as it goes around in the daylight, it just kind of gets washed out with the ambient light there. Right? We need it to be dark so that light reflecting off of it is noticeable, visible. Hey, last question. Goodness. Taking us a half an hour here. Everybody could have had this done last night. This is all the time that it takes to do it. 3 objects are placed in a row. Here's 1, here's 2, here's 3. Let's name the first one Object 1. Let's name the second one Object 2. What do you want to name the third one? 3? Oh, that's a good idea. Good idea, Julia. Let's name it Object 3. The first one is 100 kilograms. The second one is 150 kilograms. The third one is 160 kilograms. This is 10 meters distance. This is also 10 meters distance. We're trying to find the force on the middle one right here due to the other two. Well, we know that object number 2 is pulled towards object number 1. We're calling that F21. 2 is pulled towards number 3. We'll call that F32. Sorry, this is a mistake here. This shouldn't be F21. This should be F12. The force of 1 on 2. 1 pulls 2 to the left. 3 pulls 2 to the right. Now, what happens to number 1? Pulled this way, right? But who cares? What happens to 3? It's pulled this way, but who cares? We're not trying to find the force on 1 or 3. We're trying to find the force on 2. Well, let's calculate F12 and F32. Okay, we plug in our numbers in for F12. 100, 150, 10 meters works out to be a force of 1.0005 times 10 to the minus 8 newtons. F32. Masses are different here, right? Masses are different. Works out to be 1.6008 times 10 to the minus 8 newtons. So what do you got, F12 plus F32? 1.005. Is that right? Is that right? Add them up, 2.6 times 10 to the minus 8. Oh boy, that's wrong. What's wrong? Yeah, let's make F12 a negative value because it's to the left. If you want to make the other one negative, that's okay. But usually the one to the left is negative. So do the math there. We got 6.00 times 10 to the minus 9 newtons. All right. How do you guys feel about this? Is this easier than the last unit? I don't think there's any question it's easier than the last unit. There's some stuff in there that you got to know, obviously, but there's a lot less stuff. And some of the stuff in the last unit, right? Like those inclined planes and stuff, like it seems to me to be trickier than this stuff. I think this is easier. I think we should have a good chance here tomorrow to, if you went down on the last test, to bring that bar back up, I think, on this test. Pardon me? Absolutely, absolutely. Okay, that's a really good point. Watch your units, as you always have to do. Watch your units. Also watch R. Okay, how many times have we seen where you have to add a radius of a planet, or you even have to subtract a radius of a planet, or sometimes you don't need to add or subtract. Or okay, you're dealing with R. Pay really close attention to what number you need.